In our last video, we started talking a bit about compounds in general and then focused in on ionic compounds. And so let's just take another second to look at the difference between the two. Remember, in an ionic compound, ions are going to form by essentially the giving away of electrons. And so in this case here, sodium has given away one electron to form a 1 plus cation. Chlorine, you can visualize as having gained that electron to become a 1 minus anion. And so then the two of those are going to stick together. It's also important to note that ionic compounds are not discrete molecules. It's not like you have an Na and a Cl right here, and an Na and a Cl right here, and an Na and a Cl over here. What you really have is this lattice structure, and our formula gives us the ratio of those ions within that whole entire lattice. That's different from covalent compounds. So in this example right here, we have a water molecule, we have an oxygen atom, and we have 2 hydrogen atoms. And we can see the oxygen with its 6 electrons here in blue. In order to get its full outer shell, it's going to share the electrons with hydrogen. And so rather than giving away, we're sharing electrons here, and that's going to cause the elements to stick together. Now, the chemical formula for a covalent compound does show what the formula is for a discrete molecule. In this case, we would have an H2O molecule here, an H2O molecule here, an H2O molecule here, and so on. Same with glucose. Chemical formula of glucose is C6H12O6. That tells us that in each individual glucose molecule, which does exist as discrete molecules, single molecules by themselves, the chemical formula is that C6H12O6. And so each of those separate glucose molecules consists of 6 carbons, 12 hydrogens, and 6 oxygens. That's why you don't reduce the formula down with a covalent compound the same way that you would with an ionic compound. Key difference there. Now, hopefully one of the things that you're asking yourself that we haven't talked about yet is, well, how do you know what type of bond is going to form? The simple basic rule of thumb that we're going to go by is that if a metal, so remember metals are anything over here to the left of our dividing line, here's our metalloid dividing line here, anything over to the left is a metal. When a metal comes together with a non-metal, or if a metal comes together with a polyatomic ion, another reason why it's important to know those. So a metal with a non-metal or a metal with a polyatomic ion, that will be an ionic compound. If all of the elements in your compound are non-metals, that's going to be a covalent compound. So that's how we can tell what type is actually going to form. And so in this video, we're going to focus in now more on covalent compounds. We find a lot of variety with covalent compounds. The reason being that for instance, with ionic compounds, the way that they come together is going to be dictated by what the charge is on the compound. We don't have that same restriction anymore. And so covalent compounds and nonmetals can come together in a variety of different ways. And so we just end up having a lot more variety with the types of compounds that can form. So as we mentioned, nonmetals will achieve their valence shell by sharing electrons. That's a covalent bond. One paired share of electrons is a single covalent bond, and we'll look at examples of multiple bonds in a little bit. And actually, we don't really need to talk about anything else on that slide. The molecular formula typically is in alphabetical order for a covalent compound. The molecular formula can't be changed without altering the identity. Actually, we don't really need to get into that. And naming, we'll talk about in a completely separate lecture. So there we go, breezing through a lot of this. One of the ways, or one of the main ways that we show how a covalent compound is actually put together is through the use of what we call a Lewis dot diagram, or a Lewis structure. A Lewis structure shows us how all of the atoms within a covalent compound are actually arranged. And so, for instance, here we see methane. The chemical formula for methane is CH4, 1 carbon atom, 4 hydrogen atoms. These Lewis dot symbols that you see here, that's the element symbol with the number of valence electrons around it. And so if we just blow that up a little bit, so for instance, for carbon, so remember we saw how to count the number of valence electrons. I think we went over that in another lecture. If we didn't, actually, let me bring up a periodic table for us to peek at real quick. Which one do I want? I'll bring up. Sorry for the delay. Let's go ahead and just bring this up here. I think that this was on another slide, but it bears definitely going over once again. It was in a slide in a previous lecture. But, so remember, the way to tell the number of valence electrons is by looking at essentially just what column are we in. And so skipping the transition metals, we'll skip this section for now for our counting of valence electrons, because those get a little bit funky. So if we're not considering our valence electrons, our transition metals, to find your number of valence electrons, you literally just count over what column you're in. Everything in this column here, 1 valence electron. Everything here, 2 valence electrons. Skipping our transition metals, 3 valence electrons here. Actually, I forgot I could highlight, can't I? 1 valence electron in this column. Getting fancy now. 2 valence electrons in here, and so forth. 3 valence electrons. Oh, can't get too fancy, I guess. It's messing with me. Anyway, sorry, you get it. 3 valence electrons in this column, 4 in this column, 5 in this column, 6 in this column, and 7 in this column, and so forth. And so that's how we tell how many valence electrons are in an atom. And so carbon, 1, 2, 3, 4, is going to have 4 valence electrons. And so to look at the Lewis structure for carbon, we write it like this. And we always go around like that when we're doing the Lewis structure, or the Lewis diagram of a single element. Hydrogen has 1 valence electron. And so these are Lewis dot symbols for carbon and for hydrogen. And so then when they come together, they're going to come together in such a way. Actually, let me go ahead and I'll make my hydrogens red instead. Give hydrogens red electrons. And so now hydrogens are all going to come in. And there's our Lewis dot structure for CH4. We will also, though, typically, because what's happening now is these electrons here, each of these pairs form the basis for our covalent bond. So each of those is a covalent bond, each of those pair of electrons. And so normally what we do is, instead of representing them as the dots, we'll represent each bond as one line. So each of those lines is a covalent bond, and it means that we have 2 electrons there. And that's the very basics of a Lewis dot structure. We're going to look at a lot more detail here in a minute. Yep, actually nothing I need to talk about there. Okay, so Lewis dot structures. Let's look at some more details here. So like I mentioned, they're structures that represent how the molecules are bound together, and they show all the valence electrons, both what we call bonding and the non-bonding electrons. And so here with hydrogen, H2, this line here, this covalent bond represents our 2 electrons. Those are bonding electrons because they form the bond between the 2 hydrogens. And here we have Cl2. So between the 2 Cls, we have a bonding pair of electrons. Anytime you might see a little glitch like that, by the way, that just happened, it's not a glitch in the matrix. I sometimes pause the video, for instance, right then when I had to sneeze, which you didn't need to see. And so we have our bonding pair of electrons here with chlorine. We also have our non-bonding electrons around each chlorine. These are what we call lone pairs, and we'll see how to determine those and where those are in just a minute. And so how do we write Lewis structures? To write a Lewis structure for various compounds, you want to follow this very systematic and stepwise plan. The first thing to do is to identify the number of valence electrons total in the whole compound. And so we look on the periodic table for PCl3, and we see that phosphorus has 5 valence electrons. Chlorine has 7 valence electrons, but we have 3 chlorines total. And so that's a total of 26 valence electrons that we have for PCl3. Now, if you're working maybe with a polyatomic ion that you're finding the Lewis structure for, if it's an anion, add 1 electron to this total count for each negative charge. So for instance, if you're doing the count for, if you're trying to do the Lewis structure for our carbonate polyatomic ion, CO3 with its 2 minus, you're going to have carbon with its 4 electrons. Oxygen has its 6 valence electrons, but times 3, because we have 3 oxygens. And so we would have our 4 plus 18, we would have 22, but we're going to account for this 2 minus by adding an additional 2 electrons, and so we would have a total of count of 24 for CO3, 2 minus. So that's what that means here. And if it's a polyatomic cation, then we're going to subtract an electron for each positive charge. And so we've got our total electron count now. And so the next thing that we're going to do is we're going to put our compound together by putting first what we call the least electronegative atom in the center. We're going to actually talk more about electronegativity later, so don't worry too much about this now. For now, just know that most commonly, the atom that's going to go into the center is the one that just makes sense. If you have PCl3, phosphorus is probably going to be the middle one, with the other ones hanging on the outside. H2O, 2 hydrogens and 1 oxygen. The oxygen's probably going to go in the middle. And CH4 or CCl4, the carbon's probably going to go in the middle. So just put the one in the middle, put the one central that makes the most sense. And then you're going to connect, you're going to put the others around on the outside, and then you're going to connect each of those to the central atom with 1 bond. Now we have to remember that each of these bonds represents 2 electrons. So let's keep track of our electron count. We've placed 2, 4, 6. We had 26, we've placed 6. We still have 20 more electrons that we need to place. And so we're going to start that process then. We're going to place those by now filling the octets of other atoms. An octet, as the name implies, especially when you're doing Lewis structures, an octet means that you have 8 electrons. So every atom wants to have 8 electrons around it. The exception, I think I forgot a C in there, but there we go. The exception is for hydrogen. Hydrogen will only ever fit 2 electrons around it, ever, ever, ever. So an octet for hydrogen really means 2. So keep that in mind. So we're going to place these electrons around to fill our octets for every atom. So every atom wants its 8 electrons. We start with the outer atoms first. So we're going to fill up the octets of the outer atoms. So we're going to put another 6 here around chlorine. It already has 2. It's got these 2 from this bond. So 2, 4, 6, 8. And then we'll do that to the rest. So now we've placed another 2, 4, 6, 8, 10, 12, 14, 16, 18. So now we still have 2 more though. So what we'll do now with those 2 is now we will fill the octet of the central atom. We'll place these 2 on the central. And so now we have a full octet. 2 overriding rules for Lewis structures. So when you're forming Lewis structures, when you're practicing with this, when you're doing this later on, we have 2 overriding rules that basically rule everything. 1, use all electrons. Make sure that you're doing your electron count and that you're placing all the electrons and only that amount of electrons. You can't add more just because you think you need them. If you run out, you run out. And we'll talk about how to deal with that in a second. The other big rule, every atom gets an octet. Remember that an octet really means 2 for hydrogen, but 8 for everything else. So let's see if we've hit those rules with our structure here. Have we used all of our electrons? We determined that we had 26 valence electrons to deal with here. So let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26. Sorry, I just lost count a little in my head. But we have our 26 electrons around this structure. Sorry, lost count in my head. But yes, so we have our 26 electrons around this in our whole entire compound. Does every atom have an octet? Around each chlorine, we have 2, 4, 6, 8. So all the chlorines have an octet. Around our phosphorus, 2, 4, 6, 8. So boom, this is a valid Lewis structure then. We've used all of our electrons, and every atom has an octet. Now sometimes, in the case here of HCN, you might run out of electrons before every atom has an octet. Let's run through this example. So HCN, hydrogen cyanide, hydrogen has 1 valence electron, carbon has 4, nitrogen has 5, so I have 10 total electrons that I have to deal with. In a case like this, it might not be clear which one is central, and so go with, until we learn about electronegativity in a couple lectures from now. And so for now, go with the way that it's written. So I'm going to put my carbon central, I'm going to put hydrogen, and I'm going to put a nitrogen. Then I'm going to start by joining those with single bonds. And so now I've used 4 electrons. I have 6 electrons left. And so I'm going to place those as lone pairs to fill the octets of my outer atoms. Hydrogen has an octet. Remember, hydrogen's octet is 2. So it has 2 from our bond right here. And so I'm going to place those 6 all around nitrogen. So now I've used all my electrons. I cannot add in any more. And so we've hit our first rule. We've used all of our electrons. Our second rule, though, every atom gets an octet. Hydrogen has its 2 electrons. Hydrogen has its octet. Nitrogen, 2, 4, 6, 8. Nitrogen has its octet. Carbon only has 4. So carbon does not have an octet. So when you run into this, when you run into a situation where now I've used all of my electrons, but my central atom does not have an octet, steal electrons from one of the outer atoms so that it's no longer a lone pair, but it's now a bonding pair to form what we call a multiple bond. And so I'm going to steal this pair of electrons here and put those into an additional bond between the carbon and the nitrogen. So now I have what I call a double bond between carbon and nitrogen. And I still have my 4 electrons around nitrogen, my 4 lone pairs. Now carbon has 2, 4, 6. Still not enough. So I'm going to steal another lone pair to form what I call a triple bond between the 2. Now let's see if I've hit all my rules. 2, 4, 6, 8, 10. I've used all of my electrons. Hydrogen has its 1, 2. There's hydrogen's octet. Carbon has 2, 4, 6, 8. There's its octet. Nitrogen has 2, 4, 6, 8. It has its octet. Now I have a valid Lewis structure for HCN. I believe the rest of my slides here just go through those examples, and sure enough, it does. And so that's it for Lewis structures. Again, be aware that on the website, a couple things that might help you out. One is that there is another supplemental video here that does just go through. And for some reason, some of my videos on YouTube have ads now. I guess I'm popular. But there's another video here where you don't have to actually see my face, just hear my voice. But I go through several more examples and I go through all the rules. And so you might find this video helpful to just help some more with some of the various Lewis structures. There's also a couple of practice websites. And these are just websites that I found that give some good practice. And so those are definitely a place for you to practice some of your Lewis structures as well. And so that's it for covalent compounds. In our last video about compounds and molecules, our last video that pertains to chapter 3 in your book, we're going to talk about the naming of chemical compounds. And so in the meantime, as always, you stay classy, USM.